One of the most famous examples of a truss structure is the Eiffel Tower. Another example would be a crane vehicle. The bars of a structure like this must be designed in a way to ensure maximum stability while carrying a load on the crane arm. In this video we will investigate how to determine such an optimal truss design. Welcome to the search for the optimal truss. Hello and welcome to this video. We start with an introduction about the truss topology design problem. A very intuitive way to explain this problem is to think about a situation where you're an engineer tasked with designing the bars of a truss structure to which a boxing bag will be attached. Now the amount of metal that you can use for the bars is limited, and you want to distribute this material in such a way on the bars so that it will be maximally stable if the boxing bag will be attached to the blue node. For this purpose a ground structure is required, which describes which bars are available. Here for example 3 bars that are attached to the wall and the ceiling. One idea now for example would be to distribute the available material evenly across all these 3 bars. Or another possibility would be to remove some material from the bars on the left and on the right and to add this material to the bar in the middle. Alternatively, you could also distribute the total volume evenly among the bar on the left and the bar in the middle. As an engineer in this situation, it is essential to have a clear understanding of the following questions related to truss optimization. First of all, what exactly is a truss? What does it mean for a truss to be stable? And how do we obtain a stable truss design? We consider now the exact definition of a truss in this video. A truss is a structure consisting of thin bars that are connected to each other through so-called nodes. As you can see in the picture, some of the nodes in the truss are colored differently. On the one hand we have the red nodes, which are called fixed nodes. These nodes are connected to the surrounding and cannot move. On the other hand we have the blue nodes, called free nodes, which are flexible. These nodes can change their positions if a force is applied to them. In this video, forces can only be applied to the blue nodes of a truss, not on the red nodes or anywhere else on a bar. What you see currently in the animation is a ground structure of a 3-dimensional truss. Such a ground structure can be chosen as desired, so we can for example add also some more bars here. In the real world, such a truss could be attached to a wall through the red nodes, and the boxing bag could be attached to one of the blue nodes at the bottom. To illustrate the truss topology design problem again, let's choose a ground structure that contains only 3 bars. The goal now is to dimension the given 3 bars such that the resulting truss is the most stable among all other possible combinations when the force or the bag is attached to the truss. You can guess that there are many possible combinations here, and that solving this problem in general won't be that easy, especially for a large truss. In this video we will focus on 2D trusses, which are 2-dimensional trusses where all members, or in other words all bars, lie in a 2-dimensional plane. Those ones are just simpler to analyze, and the key concept of the truss topology design process is easier to understand. Note that each bar in such a truss has its own unique number, and the volume of each bar is stored in a vector t. T1 represents obviously the volume of bar 1, T2 represents the volume of bar 2, and so on. These are obviously the design variables of the truss, which are unknown at the beginning and needs to be determined through the truss design process. Through this video we will explore various truss structures, including some with over 1000 bars. The process here is always the following. Once we have constructed a desired ground structure and determined the force which will be applied to either one specific blue node or to multiple blue nodes, we will calculate the optimal distribution of the given material, which is obviously bounded, within the truss to achieve the maximally stable truss to withstand the considered forces. So now we have clarified the definition of a truss for this video and the way a truss will be modeled. To answer the second question, which was what does it mean for a truss to be stable, or in other words, what is a measure for stability of a loaded truss, we have to consider the forces inside of a truss first. So let us investigate the internal forces of a truss. Since a truss is made up of bars, let us start with the behavior of the internal forces of a bar on which a load F will be applied from both sides. Once the forces will be applied to the bar, the length of the bar will change from L to L plus delta L, where delta L describes the elongation of the bar. The bar's tendency to stay in its current position and resist deformation will be realized by the action of internal forces. These internal forces counteract the external loads applied to the bar, striving to maintain the equilibrium and stability of the structure. If we mentally cut the loaded bar in the middle, we can visualize the forces that are holding the bar together at the center. In simple terms, there will be a force applied on every atom or molecule inside of the bar at the center. This force is known as tension or stress sigma, measured in force by area. This tension sigma can be summarized as a force N. Basically, the behavior of a bar out of metal to which forces will be applied to has some similarities with a spring to which forces will be applied to. If a spring will be stretched by a relatively small distance due to external forces, it will return to its original size if the stretching hasn't exceeded a certain threshold and the external forces stop working on it. This behavior is called an elastic behavior. Note that if a certain threshold will be exceeded during the stretching process, then the spring won't have this elastic behavior anymore. The behavior of a bar under stress is now quite similar. When a force will be applied to a bar from both sides, the bar will stretch and the tension inside of the bar will also increase linearly following concepts such as Hooke's law as the elongation becomes larger. If the stretching hasn't exceeded a certain threshold, the bar will also return to its previous form after the forces stop working on it. The linear function you see here has a slope of delta sigma divided by delta epsilon, where epsilon is defined by delta L divided by L. It's important to understand that this function is only linear in the range where the elongation is very small. After the elongation exceeds a certain threshold, strange things will happen as the bar will become irreversibly stretched and ripped apart. For additional information, you can search for a tensile test. Nevertheless, the slope of the corresponding linear function describes a specific material property known as the E modulus or Young's modulus. It's important to note that the slope of this function and therefore the E modulus will vary for different materials and can be found in relevant literature or in the internet. By the definition of the E modulus, we obtain another formula for the stress or the tension inside of the bar, which is that sigma is equal to E times epsilon, and this is equal to E times delta L divided by L. And now we have two formulas for the tension sigma. On the one side we have that sigma is equal to E times delta L divided by L, and on the other side we know that sigma is equal to N divided by A. N is here the summarized force inside of the bar and A is its cross-sectional area. Our goal now is to derive a simple and useful formula for N. In the following we consider a bar connecting two free nodes V and W. The previously seen formula tells us that sigma VW is equal to NVW divided by AVW, and therefore we can calculate NVW by sigma VW multiplied with AVW. And now we can use that sigma VW is equal to E multiplied with delta LVW divided by LVW. Thus we obtain that NVW is equal to E multiplied with delta LVW divided by LVW multiplied with AVW. Now we can use that the volume TVW of the bar connecting the nodes V and W is given by the length of the bar multiplied with its cross-sectional area, so that we can replace AVW with TVW divided by LVW in the equation on the right. This is now a formula for the normal force inside a bar connecting two arbitrary free nodes V and W. We can observe immediately that the normal force depends linearly on delta LVW. Although the internal force NVW depends linearly on the elongation delta LVW, the term delta LVW itself is not easy to handle, as it is defined by the length of the stretched bar, that is, if the bar will be represented as a vector, the norm of the stretched bar minus the norm of the bar before the application of forces. So a nonlinear term. For this reason it makes sense to approximate this term using a first-order Taylor approximation. Imagine you have a bar connecting the nodes V and W and that these nodes have been displaced by forces by the vectors delta W and delta V to W plus delta W and V plus delta V. The following statement shows that if these displacements are very small, then delta LVW can be approximated by the scalar product of W minus V and delta W minus delta V divided by the length of the bar, which is represented by the norm of W minus V. If you're curious about why this equality holds, you can pause the video here and read the proof. Now we can take our previous formula for NVW and here we can replace then delta LVW. More precisely, we can replace delta LVW with the first order Taylor approximation from the previous statement. Now remember that the force has a direction and a magnitude, what implies that the force can be represented by a vector. But up to this point, NVW is only a number representing the magnitude of the internal normal force NVW. Given the video's precondition that forces can only be applied to the blue nodes and not on or inside a bar, we will model an internal normal force on both nodes W and V when considering only one bar connecting these two nodes in a truss. Without loss of generality, we will consider here the normal force from node V to W. This force can be represented or modeled by a vector that goes from V to W and has a norm of NVW. So what can we do now? We can just take the scalar NVW and multiply this scalar with the vector W minus V divided by the norm of W minus V. So the normalized vector that goes from V to W. The next two steps are just simplifications. Note that at this point the vector W minus V divided by the norm of W minus V squared has been defined as BVW of W, and minus this vector has been defined as BVW of V. Basically, we define such a vector BVW for every bar in the truss that is connecting two nodes. This vector has always 2 times k entries, where k is the amount of free nodes in the truss. Nearly all entries in a row of this vector will be 0 instead of those entries that are in rows corresponding to the nodes V and W if V and W are free nodes. For the case that V and W are both fixed nodes, then this vector will only contain zeros. But for a bar that is connecting two free nodes Vi and Vj, the vector BVI-Vj will look like this. So we see every free node has its own 2 rows in this vector, and the entries that aren't 0 can be calculated by the previously shown formula. I have to admit that this formula looks a bit complicated, but don't worry, there will be an example in a few minutes that should bring more clarity. For the scenario where we assume a given truss has k many free nodes to which forces can be applied to, we define a vector f containing k vectors from R2 and additionally to this a vector delta capital V representing the corresponding displacements of these k nodes. With these definitions we can simplify the right-hand side of the above equation even further. So what we obtain is the vector representing the internal force from the node V to the node W is given by minus E multiplied with BVW of V multiplied with TVW and then with a scalar product of BVW and delta capital V. So this is a formula for the normal force at the node V along the bar from V to W in a loaded truss. Our next goal is to calculate the total force in a truss that works on the node V. As you can probably imagine, there will be a bunch of nodes in a truss on which internal forces will work on. Also note that contrary to what is depicted here, no forces will act on fixed nodes. Internal forces can only affect free nodes. Well, now let us consider a simpler example. Given the following truss to which a force F will be applied to the node V. How can we calculate now the total internal force working on this node? Given the above formula, this is quite simple because we just have to calculate the internal force that is working from the node V to W1 plus the internal force that is working from the node V to W2 plus the internal force that is working from V to W3. So in general we can say that to calculate the total force that is working on a free node V, we have to sum the above formula up, and this for all W in U of V, where U of V describes all nodes that are connected to the free node V. For all free nodes V1 to Vk, we save the corresponding internal force in a vector n truss. For every entry in this vector we can insert now the previously calculated formula, and then we can pull the minus sign out as well as the vector delta capital V. We define the matrix here as K of T, which is a quite famous matrix because this is the stiffness matrix of a truss. It can be shown that the stiffness matrix of a truss can be written as a linear combination of other matrices, and denotes here the set containing all nodes of the truss. Furthermore, it can be shown that the stiffness matrix is equal to E times B times diag of T times B transposed. Diag of T describes here a diagonal matrix containing the vector T with elements T1 to Tm on its diagonal. The matrix B is the so-called node bar matrix that contains all vectors BVW column-wise, and E is the E modulus. At this point let us do a short example to reinforce what we have seen so far. We consider the following two-dimensional truss with nodes from 1 to 6. They will be always numerated from the left to the right, row by row. As you can see, we have 4 blue nodes in this truss, so we have 4 free nodes V1, V2, V3 and V4. I mentioned before that to calculate the optimal truss, we will have to calculate the vector BVW for every bar in the truss. The matrix B that contains all these vectors column by column looks like this. The truss that you see in the background has a height of 1 meter, a width of 2 meters, and the corresponding unit used here is centimeter. And as I mentioned before, every free node V1 to V4 has 2 corresponding rows in each vector BVW. If you want to define a force that will work on this truss, you will have to define a vector with 8 entries. In this case, the vector F is made up of 4 vectors from R2, F1, F2, F3 and F4, and what this means is that the force F1 will be applied to the node V1, the force F2 will be applied to the node V2, and so on. An obvious observation is that if a force F will be applied to a bar, that then the internal force N inside of the bar will have the same magnitude as the force F. In other words, the system here is in equilibrium, meaning that N is equal to F. For an entire truss, this implies that the sum of all internal forces and external forces must cancel out to withstand the working load. This means that N truss plus F has to be equal to 0. Now remember that n-truss is equal to minus the stiffness matrix multiplied with the displacement vector delta V. In summary, we obtain that in order to prevent the truss from destruction, the condition that k of t times delta capital V is equal to F has to be always fulfilled. This system of linear equations in matrix representation represents the so-called conditions of equilibrium. Now that we are aware of a necessary condition that must be fulfilled by t and delta capital V, we are a step closer to the formulation of our first truss topology design problem. The questions we haven't answered so far are questions like what does it mean for a truss to be stable, or what is a measure for the stability of a truss? It is crucial to determine such a measure for the stability of the truss, as this will be the term that we will optimize. And this measure is given by the potential energy stored inside of the truss while the forces are working on it. We refer to this potential energy as the compliance. So in simple terms, we can say that the work performed by a truss under a certain load is a measure for the stability of the truss. Just as a spring is considered as stable if it does not stretch too much under the influence of certain forces, a truss is considered as stable if it undergoes small deformations when certain forces are applied to it. First of all, we will begin by calculating the work carried out by the bar connecting nodes V and W, which has been stretched by the distance of delta LVW due to external forces. We denote this work as WVW, which can be calculated through the integral of the magnitude of the internal normal force over the distance of elongation. The remaining steps are just straightforward simplifications. After a few simplifications, we obtain that the work carried out by the bar connecting the nodes V and W is given by 1/2 multiplied with E multiplied with T VW and the square of the scalar product of delta capital V and BVW. To obtain the work carried out by the whole truss, we have to sum this term up, and this for all nodes V and W in the truss. Note that the set of all nodes is denoted here by n. Note also that we call this work here C index f of t, what stands for the compliance of the truss with the volumes from the vector t under the load F. After a few simplifications and under the consideration that k of t multiplied with delta capital V has to be equal to F, we can derive a short term that describes the compliance of the entire truss under the load F. This term is given by 1/2 multiplied with F transposed multiplied with delta capital V. And now we have everything we need to describe our first truss topology design program. The goal here is of course to find a volume vector t and a vector delta capital V such that the compliance of the truss will be minimal. The conditions that the truss with the volume vector t and the displacement vector delta capital V has to fulfill are the following. The truss must satisfy the conditions of equilibrium, meaning that k of t multiplied with delta capital V has to be equal to F. The sum of all entries in the vector t must be less than or equal to the volume bound V bar, and the volume of each bar in the vector t must be greater than or equal to 0. Note that this program will search for a volume vector t and a displacement vector delta capital V, which describes the displacement of every free node in the truss with the volume vector t under the load F. This problem itself is nonlinear, and in many papers a transformed version of this program has been used to determine an optimal truss design. Basically, this program can be reformulated as a semi-definite program, also called an SDP-Program, which in this case becomes a linear program with an additional constraint involving a matrix that must be positive semi-definite. This transformation is exactly what we are going to investigate now. The first statement we need for the transformation is that the stiffness matrix K of T of any given truss is positive semidefinite. This means that x transposed times K of T times x is greater than or equal to 0 for all x that are unequal to 0. Well, for x equal to 0 this is true anyway. The proof for this is straightforward. Basically we write the stiffness matrix K of T as E, B, square root of D, square root of D, B transposed. Then we shift B square root of D into the other component of the scalar product. For this we have to transpose this matrix. And at the end we obtain finally a norm here, and the norm is obviously greater than or equal to 0. Using this statement we can conclude now the following. K of T is positive semidefinite. This implies that the function h of x defined by x transposed K of Tx is convex. But then is the function minus h of x concave. But then is also the function phi Tf of x defined by f transposed x minus 1/2 x transposed K of Tx concave. The reason for this is that the function defined as the sum of concave functions is concave again. Now let us take a look at the gradient of this function. What is the gradient of this function? Well, the gradient of this function is f minus K of T times x. The concavity of phi implies now that the function phi is bounded from above if and only if there exists an element x star from Rd so that f minus K of T times x star is equal to 0. But this is the case if and only if x star fulfills the conditions for equilibrium. So what does this mean now? This means that the maximizer x star of phi Tf satisfies always the equilibrium conditions. On the other side, if there exists such a maximizer x star, then we can also calculate the corresponding maximum value of the function phi. And what a surprise, the maximum value of this function is exactly the compliance. So 1/2 f transposed x star, where x star is the displacement vector. A thing that you should remember here is that this function phi is upper bounded if and only if the compliance, so Cf of t, is upper bounded by a number w. This implies then that for a specific bar volume vector t, there exists a maximizer of the function phi, which is the displacement vector that satisfies the conditions of equilibrium. Well, and how do we get now to a semidefinite program? Well, the condition that phi is upper bounded by a number w is equivalent to a specific matrix being positive semidefinite. And this is the next and the last statement of this video. The statement says that if we consider the stiffness matrix of an arbitrary truss with a volume vector t and a force F, that then we have the following equivalence for the previously defined function phi. The function phi Tf of x minus w is smaller or equal than 0 for all x element Rd, so this means that phi Tf of x is upper bounded by w, if and only if the following matrix is positive semidefinite. Now you have the choice to either watch the proof or to skip it for now and to return to it after the end of the video if you're interested. A short remark before we jump to the SDP program now. Note that it does not matter whether we minimize CF or 2 times CF. According to the last statement, a minimization of 2 times CF is possible if the following condition holds. Okay, now let us consider the SDP program. The term that should be minimized is the upper bound for the compliance W, and the constraint K of t times delta capital V equal to F will be replaced with the following matrix being positive semidefinite. And same as before, the total volume for the truss is upper bounded by a volume bound V bar, and every bar volume has to be greater or equal than 0. Of course, you can also rewrite T as A times L anywhere in the video and also in this program here, and then you can optimize the cross-sectional areas of the bars instead of the volumes. The result is then obviously the same. Note that if you calculate a solution with this program, you will obtain on the one side an upper bound for the compliance, and on the other side a volume or a cross-sectional area vector. In contrast to this, the previously considered TDD program has also calculated the displacement vector delta capital V. In this case, if you only have the volume vector t, then you can calculate also the displacement vector through the system of linear equations K of t times delta capital V equal to F. In the following, we will consider an implementation of the right program that you see here in Matlab. The first question now is, how can we solve such an optimization program? The easiest way to solve such a program is with modeling languages like CVX or YALMIP. First we will consider now an implementation using CVX and then an implementation using YALMIP. All implementations here require that you have already created a truss object referred to as truss with attributes such as arrays containing nodes and bars, the corresponding matrix B, and the E-modulus of the material being used. Basically, the code here is made up of 2 parts. The first part involves extracting all the necessary properties for the calculations, and in the second part a solution for the optimization program will be calculated. From line 6 to 7 we initialize a vector C containing the length of every bar in the truss, the amount of bars M, which is then given by the length of the vector C, and the number D, which is equal to 2 times the amount of free nodes in the truss. Please note that the vector C in this example is a row vector and not a column vector. In line 9 and 10 we extract then the node bar matrix B and the E-modulus of the used material from the truss object. With the code from line 17 to 24 we can solve then the optimization problem using CVX. The code starts with CVX begin, then we have the command quiet to suppress the solver output. After that we have to define the variables, so the optimization variables, which are W and A, where A is a M times 1 vector, and the optimization program is to minimize W subject to the following constraints, and after that we have to insert the code CVX end. To solve this program with YALMIP, we have to define first SDP variables W and A of the corresponding size. Then we have to construct the constraints, so in this case model describes the constraints for the optimization problem, and then we can solve this problem with optimize of model, W. Now let us take a look at a few examples. First we consider now the following truss to which a force F will be applied to. The force F here is made up of the forces F1, F2, F3 and F4, and the loaded node is the node V2 on which a force will work vertically downwards with a strength of 100 kN. Note that the nodes in a truss are always numbered from left to right and this row by row starting from 1. Furthermore, it's important to observe that the blue nodes representing the free nodes are numbered from V1 to Vk if a truss contains k free nodes. In the app that you can see in the background, I will select for every example a ground structure and a node from the truss by the selection of a number that represents the node associated with the corresponding number, and then I will optimize the ground structure for a certain force working on this node. I will use here a slightly different notation that F index I stands for the force that will be applied to the node I. So for example, in general, F3 does not mean the same as capital F3. This is because capital F3 is the force applied to the free node V3 and F3 is the force applied to the node with the number 3. So please be cautious not to confuse the force Fi with the force capital Fi. Okay, now let us optimize the 2x3 truss here for the force Fi. The volume bound V bar is given by 500 cubic centimeter. And the node to which this force should be applied is the node I, and I has to be equal to 3, because we want to apply this force on the node 3. Or more accurately, we want to optimize a truss with the underlying ground structure with this specific volume bound if the force Fi will be applied to the node 3. This is then the corresponding optimal truss, and at the bottom you can also see a value for the compliance given by W. And by the way, the unit of W is given by joule, and the actual reaction of the truss, if the given force will work on it, looks like this. Keep in mind that this is the optimal solution for the truss design considering the given ground structure. In other words, if exactly this force will be applied to this truss, there is no other configuration that would result in less deformation. It's important to note that the actual force applied to the truss should not vary significantly from the force for which the truss has been optimized. For the next example, let us increase the volume bound to 1500, the height to 3, and the width to 4, and also the maximal length of a bar to 4. Now we want to find an optimal distribution of the material for this ground structure and if the force Fi will be applied to the node number 8. This truss has 3 times 4 equal to 12 nodes and 9 of these nodes are free. Since this truss has 49 bars, the corresponding matrix B is a 18 times 49 matrix. Nevertheless, thanks to efficient solvers and fast computers, this truss can be optimized in less than a second. And I'm pretty sure that you would agree that this solution does not look that obvious. Well, now imagine optimizing a 10x10 truss with over 1000 bars. The node bar matrix B for this truss is a 180 times 1106 matrix. A matrix with nearly 200,000 elements. While this might sound incredibly large at first, it's not considered as a problem for an SDP solver. In fact, we obtain a solution here in less than a second. In my opinion, this is quite fascinating. Just for comparison, this is a 180 times 1106 grid of dots. The entire grid represents the size of the node bar matrix B, with each dot symbolizing an element of the matrix B. This is incredibly large, and the computer solves the corresponding optimization problem in not even a second, while it calculates also this matrix. Absolutely fascinating. Although our truss program calculates the optimal truss for a given ground structure, the solution seems a bit impractical. At least sometimes. This is because there are very often nodes that are not fixed by additional bars, what implies a strong potential deformation of the truss if forces will be applied to these nodes. Such a truss structure is simply not robust against perturbations. A better solution would look, for example, like this. However, this is only an approximation to a more robust solution that I've calculated using a simple heuristic. And if you look closely, you will also notice that there are nodes in this truss that do not appear well fixed at all. And in general, you will have to find a compromise to obtain a robust solution. Because the more you distribute the given material on bars connected to nodes on which the considered force F won't probably be applied to in practice, the more the truss will deform if the force F will actually work on the truss. because you will simply move away from the best solution for the force F for this truss. A better example to see this would be with this power pole. First we will optimize this power pole against forces that work vertically downwards on the node 17 and 26 and have a magnitude of 100 kN. This is then the corresponding result. If we apply the actual forces on this truss, the deformed truss will look nearly similar as before. Nevertheless, this solution seems very impractical in practice with these thin legs. Therefore it makes sense to consider a robust solution. Now all nodes in this truss are fixed with additional bars and the legs of the power pole seem very solid. But unfortunately the truss deforms now way too strong if the forces will actually work on the truss. In summary, it can be said that it is in general not an easy problem to determine an optimal truss that is also robust. In fact, one will see that to really obtain a global robust solution for a certain set of considered forces, one will have to solve an MI-SDP, also called Mixed Integer Semi-Definite Program, which cannot be solved efficiently, and what shows then the dependence of an efficient heuristic to approximate a robust solution for the truss. But the robust truss design optimization would be a topic for a video itself and will therefore not be covered here. Basically the idea there is to minimize a truss not for one force but rather for a set of infinitely many forces. The term to minimize is then the worst case compliance for elements from this infinite set. With this being said, we've reached now the end of this video. Thank you very much for watching, and if you haven't already, I would appreciate if you would like this video if you found it interesting and to subscribe to this channel.